Okay, so welcome. I'm Maciej and I'm going to present the results of our work on LogGraph, a high-performance near-optimal graph representation. So as you all know, in today's world we have these large graphs that we need to process, and they can run on anything from supercomputer to a smartphone, and they also use in various domains, for example in machine learning and computational sciences and many other things. And now what is common to these graphs is that they are huge, right? So they are large, and if we take a look at, for example, some of the example graphs that we deal with these days, for example, at Connect datasets or at graphs using Graph 500 benchmark, or at some other graphs like WebGraph datasets or Web Data Commons, we can see that they are really large. So, for example, here we have like graphs that are more than a billion edges, and need somehow to store and to manage these large datasets. Right, so the traditional compression is okay, but it's quite slow. It entails, of course, the decompression overheads. So to elevate this thing, we present LogGraph, a representation which combines effective compression with low overhead decompression. So the key idea and the key question that we ask ourselves before we actually venture into this project was, what is the storage? What is the lowest storage we can hope to use to store a given graph, right? And it's of course the storage lower bound. But then the next question, immediate question, is which storage lower bound? Because of course we have a couple of storage lower bounds. So the one that we consider in this work is the counting bound, which means that we consider logarithmic storage lower bounds, in which we need log of size of s bits to store an object from an arbitrary set S that has size of S elements. So for example, here we have this element, we have set S with some elements, and if we just assign increasing bit vectors to these elements, I mean, playing with this argument, we can just see that our bound logarithmic size is the correct one. Right, so the key idea in the representation that we propose is to encode different parts of a graph using these logarithmic storage lower bounds. What I mean by saying different parts of the graph representation, I mean, for example, fine-grained elements such as vertex labels, like the ones here, or edge weights, but also coarse-grained elements, for example, the whole adjacency arrays, which means edges adjacent to each vertex, and also the offsets, which means the locations that we store each of these adjacency arrays. Right, and this means that we just want to grab all these elements and derive logarithmic bounds for all of them, and then combine them together in a single graph representation. Okay, so before we proceed, let's take a look at some of the concepts we are going to use in this talk. So what I mean by saying adjacency array graph representation? Well, if we take a look at the logical way the graph can be represented, the more abstract way, we have some vertices that correspond to the graph that we have on the right here, and then each of these vertices have some neighbors. So for example, vertex 0 have neighbors 1 and 2, and they form, each of these neighborhoods forms some kind of adjacency data structure, which is also correlated with some offset, which tells us where this data structure is actually located. And now a very popular way to implement this in practice is to use so-called adjacency array physical realization, where all these neighborhoods are stored contiguously as one huge array in memory, together with additional array that contains the offsets from the beginning of this large array to the place where each of these smaller arrays corresponding to each of these neighborhoods is located. Right, so these are these two arrays, and again, what we are doing in LogGraph is logarithmizing, as we call it, is taking the storage lower bounds and encoding them together, both for the small elements, for the fine-grained elements, and for the coarse-grained elements, such as the offsets array or the adjacency arrays themselves. Right, so let's first take a look at how do we deal with these fine-grained elements, namely vertex labels and edge weights. So here we have our graph that we considered before. This indicates that we are dealing with these small elements, and here are some symbols that we are going to use. So, like, the simplest step that you can take here is, of course, that we, in a graph that has n vertices, we use ceiling of log of n bits to store each vertex label, right? So, is it what we are really doing? Well, not really. Of course, this would be too simple to do. What we are doing is something more that we call local. As an example, as a motivating example, consider a graph that has, for example, that many vertices, and that has a certain vertex with very few neighbors, right? So the degree of the vertex for some vertex v is much smaller than n. And now what happens is that if all these neighbors have very small labels, right? If if it happens that we label the graph in such a way that the maximum label in this neighborhood is very small, then what happens is that, of course, we waste many bits. Right? So, for example, here we have that many vertices, we have that example adjacency array of this particular vertex V, and this means that we are going to use 22 in this global approach, 22 bits for each of these IDs, even though they waste many bits as unused zeros. Right? So this is bad, and this is why the first step in log graph is to use the local bound ceiling of the log of the maximum label in each of these neighborhoods, and because this allows us to alleviate this problem. We no longer has these leading zeros, at least in this example. Right, but it still doesn't really solve all the problems, or even many of them, because what happens if we have the same graph as before, and that again we have this neighborhood with very few neighbors, very small labels, but one of these labels has a very large ID. Right? So one of the neighbors has a large ID. For example, here we have this vertex V, and again the same neighborhood, but the final label has 1 million label. Right? So this is again bad, because this means that even though we use this local approach, we still waste this time only 17 leading bits in each of these IDs, right? So this is also not great. And here our solution is to approach the problem with the ILP. So what we are doing, we are trying to reshuffle these labels in each of these neighborhoods in such a way that we minimize these maximum labels in each of the neighborhoods. Right? So we're going to permute the vertex labels to reduce these maximum labels in as many neighborhoods as possible, because of course we can't really do it for all of them easily, but we can have heuristics that tries to maximize the number of such neighborhoods with minimized maximum labels. And so here again we have our example. So what we do, we first permute all these labels simultaneously for all the other neighborhoods, of course, such that we get the new labels, preserving of course the structure of the graph, hopefully having smaller labels, and even though some of them may have larger labels than before, they are going to be still much smaller, and the total gain in storage is going to be still positive. Right, so we have the heuristics, which is, and of course this, if you want to solve it using precisely this problem is NP hard. So we have a heuristics which kind of resembles the formulation of the ILP, and this heuristics is based on minimizing the following sum of the products of the inverses of the neighborhood size times the maximum labels in these new neighborhoods. And the intuition is that this is kind of inversing this degree is kind of going to motivate having these smaller labels in the respective neighborhoods. We also conduct some formal analysis. So we assume two well-known graph models, power law graphs and random uniform graphs. In power law, we have the probability that the vertex degree D is alpha D to the beta, and which corresponds to many graphs that are used in practice. In the random uniform graphs, we have of course, random uniform vertex degree distribution. So every vertex has the probability that the vertex has degree D is sum P times D. So this, and what we do is computing the expected size of the adjacency array for these two models of graphs that we consider, using the log graph formulations. Right, so we do have more of this analysis. You can check all of them in the paper, as well as an additional design where we also explicitly consider using the fact that our graph can be distributed over multiple units of a hierarchical machine such as Cray supercomputer. Okay, so what is now the key method? Because we now describe what we do, but how we actually now make sure that this is performance. So here in the part of log graph where we deal with these fine-grained elements, we use the Besta bitwise operation to help extract an arbitrary sequence of bits, because what we now really need to do is we need to be able to extract an more or less arbitrary sequence of bits from this contiguous adjacency array corresponding to a compressed bit ID, to a compressed vertex label. And so here we use this Besta bitwise operation, and the whole function is as follows. So for example, in our function NIV, which returns the ID, the label of the ith vertex in the neighborhood of vertex V, we have the following arguments: the ID of the vertex that we are considering, the ID of the sequence number of its neighbor, the pointer to the offset array, the pointer to the adjacency array, and the parameter that tells us what is the actual compression ratio, logarithmization ratio in our representation. So in the first step, we need to derive the exact offset in bits to the label of the neighbor that we want to extract. Then we must derive the closest byte alignment. We also do other alignments, but we tried them, and the difference in storage and performance differences were negligible. Then we need to get the distance from the byte alignment, and finally we can access the derived, at this time still 64-bit value, and finally we use Baxter to simultaneously shift and mask the extracted memory word to extract the desired vertex label. Okay, so that's it for the fine-grained elements. Now let's take a look at these coarse-grained elements. So how do we represent in log-graph the larger elements of the adjacency array, such as offsets or the whole adjacency data? So again, we have our graph, and this symbol indicates that now we care about these arrows, which are the actual locations, the offsets. Right, so the first step is to use a bit vector instead of an array of offsets. Right, so as we saw before, we have this huge contiguous array that corresponds to all these neighborhoods. We have the array of offsets, and here in the first step, we instead of using this explicit array of offset integers, we use a bit vector where ith set bit that has the following meaning: the ith set bit has a position x, and this means that the adjacency array of a vertex I starts at the word with the ID x. And so, for example, this set bit 1 here indicates that has the following position that you can count from this bit vector, and this means that 1 before the last adjacency array starts at this precise location here. Right. So now to be able to query these locations efficiently, we need to be able to, in a fast way, answer the question of how many ones are set before a given bit. And this is the motivation, some of the motivation for taking the next step that we did in log-graph, is to encoding these bit vectors using the so-called succinct formulation. So here, instead of just plain bit vectors, we use so-called succinct bit vectors. And here, a brief introduction on what a succinct bit vector is. So succinctness is a more general concept which is also applicable to other data structures. Namely, we say that a given data structure is succinct if this data structure uses that many bits, where the ceiling of Q is the lower bound to store a given piece of information, simultaneously enabling answering various queries in small o of this lower bound time. Right? So this intuitively means that we want to be close to the storage lower bound in our representation, at the same time being able to answer certain queries asymptotically fast. And here this was our idea, to use one of such succinct bit vectors that satisfies this condition as the way to represent this offset bit vector. So again, it's going to be hopefully small and fast, which is actually going to be the case, as we will see in the evaluation part. But before we proceed further, let's take a look at how the succinctness in this corresponding bit vector case looks like. Right, so we have our bit vector, and it has n bits, and what we do here, we divide this bit vector into smaller chunks that have a specially selected size. In this case, it's square of log n. We denote this value with t1, and then for each of these blocks, we divide them into yet smaller blocks that have also a certain size. This is 1/2 of log n, and now and we do it, of course, for all the blocks. And now the key step in this representation, this way of using the succinct bit vectors, is to compute and store the number of ones of bits that have value of 1 in each of both the large and of the small blocks. Right? So we need to pre-compute and store these values additionally together with the actual bit vector. However, the cool thing is that now, once we sum all these fractions here, so I will not go into details here, but the cool thing is that the selection of the sizes here will result in the fact that once we sum all these additional all the space that we need additionally to store all these pre-computed ones, together with the actual stored bit vector that we can now represent using a hierarchical representation based on these blocks, the total storage is actually going to be n plus small o of n. which is going to satisfy this succinct criteria. At the same time, storing these pre-computed ones enables us to have fast queries into the structure of the graph, into the structure of these bits that are set at the given location, which will in the end enable fast accesses to a given adjacency array in a given graph. Right, so we also have a formal analysis for this. We analyzed several different types of bit vectors and compared them to a plain adjacency, to a plain offset arrays. But again, details are in the paper. So in practice, this what we will show is that these selected bit vectors were both small and fast. Okay, and finally, the final element that we need to deal with is the actual adjacency data, right? So we dealt with the pointers, with the offsets. Now we deal with the actual data that we store as this one huge adjacency array. Right, so how do we approach this? In LogGraph, we use different relabelings. So what we do, similarly to the step before for these fine-grained elements, now we do it in a more global setting, considering the whole structure. We use different relabelings, and the main one that I'm going to focus on this presentation is so-called degree minimizing. So here it's a scheme where we target general graphs. So we don't make any assumptions about the particular class of the graph or the structure of the graph. I mentioned this because we also have a couple of schemes in LogGraph that have some stronger assumptions about, for example, what a graph is, I mean, what are its properties, etc., etc. But here, I'm going to skip this talk because of timing constraints. So in the degree minimizing scheme, what we do, we first permute the vertex labels in such a way that the more often the label occurs, this corresponds directly to the higher vertex degree, the smaller permuted value it receives, because intuitively if the vertex has a high degree, then it's going to be visible more often in the whole representation. So we want to reduce the space it occupies by giving it a smaller label. Right. In the second step, we gap encode the resulting permutation, which means instead of just storing the exact values of the labels, we just store only the first one, and then we store the differences between all of them, except for the first one, which is always the vertex ID, the ID of the vertex that we are considering in a given setting. Right. And so again, we encode these differences, and now let's take a look at the global again, at the whole graph from the higher perspective. Right. So because we went through a couple of different schemes, so in general, what LogGraph is a combination of some input structures, and then we have the first main part where we compress these fine-grained elements like vertex labels. In the second part, we compress offset structures. In the third part, the main one, we compress in a couple of different ways these whole adjacency arrays. And now we have these three distinctive parts, and the whole thing looks quite complex, right? So this looks not very simple to use, and because, as a matter of fact, we analyzed and implemented in total 6 schemes for compressing these fine elements, more than 10 schemes for compressing these offsets arrays, and more than 4 schemes for compressing these adjacency structures. And now using all these things together in different combinations is going to basically blow up the space of designs even farther. And but what we ensured is that we can actually combine all of them arbitrarily in a fast, manageable, and extensible way by using C++ templates that we use to implement a library which can be used to again combine these elements, and now, for example, try if for a given scheme for compressing the offsets, what is the best scheme, for example, for compressing the corresponding vertex labels, edge weights, and again the whole adjacency data as a whole. So now let's take a look at how this looks in practice in terms of the performance and storage overheads. So we conducted several experiments on different Cray machines and on a fat HP server. The types of graphs we considered are both synthetic graphs that we again analyzed also in theory, as well as various real-world graphs from Snap, Connect, WebGraph, and Emacs datasets. The algorithms we consider, because also the key interest here is to understand what is the impact on the performance of different graph algorithms while compressing these graphs. So the ones we considered are Connected Components by Shilova-Vishkin, Breadth for Search, and in which we pick some root and then proceed in steps to visit all the other vertices, as well as SSSP, the algorithm which is implemented as the solved with the delta stepping algorithm. We also considered triangle counting, where we count number of triangles that each vertex is a part of. We also considered betweenness centrality, yet another centrality metrics where we assign importances to vertices based on the number of shortest paths that each vertex is sits on the way of. And finally, we also considered PageRank, the well-known algorithm, where we also rank vertices according to how many important neighbors each of them has. So first, let's take a look at the also other comparison targets. So the first comparison target that we considered is GAPS, is a established benchmark for analyzing the performance of graph algorithms. We use it to understand how the performance of tuned algorithms changes after applying different compression schemes. In addition, we also compared to zlib, which stands for the traditional compression schemes. We considered WebGraph library, which is the state-of-the-art library for specifically compressing graphs. And we also compressed to a certain selected scheme called recursive partitioning, which represents a certain tuned scheme for compressing only the adjacency data. Okay, so first let's consider the fine-grained elements, vertex labels and edge weights. Here we are considering, again, we have more of the data, but due to timing constraints, this can be seen only in the paper or in the extended tech report. Here we consider the SSSP algorithm running on canonical graphs with that many vertices. On the x-axis we have number of edges per vertex. On the y-axis we have time in seconds to finish the algorithm, and we compare the gaps, the baseline that provides the implementation of the algorithm, together with the variant of gaps which is compressed with LogGraph. And we can surprisingly see that even though LogGraph consistently reduces storage overhead by between 20 and 35%, it also accelerates gaps. So we have both of these gains happening at the same time. So we both compress the graph and make the processing of this graph faster. And this is really cool, and this is because, again, we have this very lightweight decompression in this particular family of schemes in LogGraph, which transfer less data, which in the end results with these simultaneous improvements in storage and performance. Let's now take a look at the offset structures. How do the compression of offsets looks like in LogGraph in practice? So again, we have lots of data, but no worries, we don't really have to analyze all of these plots. What is important, which is quite generic to all the other data points, is this one particular picture here. So what we do, we compare different offset arrays with different families of bit vectors, and what is important is to realize that succinct bit vectors are definitely the smallest out of all the compared ways to encode the locations of neighborhoods. So they consistently ensured the best storage reductions. And the main reason was that these succinct designs work really well for sparse bit vectors. And again, the graphs that matter are sparse, which is, again, we have a nice way to utilize these theoretical structures to use them in a practical setting in graph compression. In terms of the performance, here we have on the x of the offset structures after compression. In this plot, on the x-axis we have number of threads that run in parallel. On the y-axis is the average query time in which we access randomly selected neighbors a selected number of times, doing this for the same canonical graphs that we saw before. And here again, these different lines of plots are different comparison targets. And again, there are many of them, so let's just focus on the ones that are most important. So the most important two parts are these parts here. So on one hand, we can see that the performance of simple offset arrays is definitely the best one if we consider the environment where we have very little parallelism. However, as we increase number of threads, overheads of parallelization kick in, and in this place we can clearly see that the performance of bit vectors is becoming similar to that of the offset arrays, especially the succinct bit vectors BVEN and BVSD that we also saw before as being very good with the storage overhead reduction. Especially BVSD was usually the fastest and usually the smallest. And so this is a nice conclusion, because again we can use this in a generic way. So we can use this way to compress offsets in many different cases, and usually having both storage and performance at least as good as with the offset arrays. And finally, for the adjacency structures, we again compare a couple of different schemes, but here again the most important ones are this traditional scheme where we only use the traditional way of storing adjacency arrays together with WebGraph, which is this state-of-the-art library for compressing graphs, and with degree minimizing schemes, the variants that use and do not use gap encoding. And again, what is the conclusion is that the WebGraph is best for, well, WebGraphs, as we can clearly see in these plots here. So these three graphs are actually WebGraphs, and WebGraph is really the smallest
However, for different types of graphs, it's okay. Then for the other schemes, this BRB and RB, these are again the specific schemes that I omit here in this. Because of the time constraints, you can check the details in the paper. What is then interesting is that DMD is much better than DMF. So the one that uses gap encoding is much better than the one that does not use gap encoding, and it's often comparable to WebGraph. So in addition, in terms of performance, we run different graph algorithms on this compressed representation. In this example, it's BFS, and we can see that that while being comparable or slightly worse than WebGraph in terms of compression, these degree minimizing schemes are much better in terms of almost always much better in terms of performance. The only case where they are not that great or comparable or slightly worse than WebGraph is here, where we process a graph which corresponds to the road network, which is understandable because then this graph has a particular different structure that we don't really focus on in LogGraph. Okay, so the takeaway is that LogGraph ensures the space performance sweet spot, which is also tunable in the space of different graph compression designs, right? Because on one hand, we can compress vertex labels, which gives us reasonable storage reductions and quite negligible decompression overheads. On the other hand, we also can use compression of offsets, which is going to always give some space reductions and be at least as good in parallel settings in terms of performance as the traditional schemes. And finally, if someone wants to go more for the compression but doesn't care that much about the performance, then they can use the compression of the adjacency data that is included in the LogGraph with much higher storage reductions and also somewhat higher performance overheads, which are still usually much better than the ones from the graph compression schemes such as WebGraph. We have also lots of other data. You can check all this data in the paper and the technical report. And with this slide, I'd like to conclude. So what we did, we designed LogGraph. And LogGraph is, what is LogGraph? LogGraph is on one hand a near-optimal graph representation because we explicitly approach the storage lower bounds. LogGraph is an extensible graph representation because we design it in such a way that you can extend this with your own implementations of compression schemes for different graph elements. It's a high performance representation because it ensures performance improvements for different graphs and algorithms. And it's a condensed representation because it also reduces storage required to store different graphs. Thank you for your attention.